Alright, so in this problem, we're told about a string that has a length of 2.70 meters, a mass of 260 grams, which I rewrote as 0.260 kilograms, and a tension in the string of 36.0 newtons. Also, the amplitude of the string, because we have a transverse wave moving through it, should be 7.70 millimeters, and an average power of 85.0 watts. Now, we have to find out what the frequency of the traveling waves would have to be in order for the average power to be 85.0 watts, and for the amplitude to be what it is. So basically, what the question is asking us is, with the variables we're given, what is the frequency of the wave? All right, now first, let's consult the formula for the average power, since we are given the formula for power after all, and it makes sense to write that out and see how that will relate to the rest of this, especially since the formula for the average power includes a lot of different variables just in that one formula. And the formula for the average power is equal to 1/2 times the linear string density times the wave speed times the angular frequency squared times the amplitude squared. So you've got a lot of different variables just in that one little formula there. But because of how many variables there are, it might not be immediately obvious how we're going to relate frequency to this. But we do have a formula for frequency that does relate directly to one of these variables, and namely the angular frequency. And that formula is the one that says that the frequency is equal to the angular frequency divided by 2 pi. So let's try and rewrite this formula, the average power formula, in terms of just angular frequency, because all the other variables we could have are given to us here, except for the velocity, actually. Because the problem does tell us the amplitude, we have that. The problem does tell us the linear string density indirectly, because it gives us the length of the string and the mass of the string. So knowing that, it'll be pretty easy to find out what the linear string density is. We don't have anything about the wave speed, though. We'll have to rewrite that bit, because we are given the tension of the string right here. And as I just explained, we will be able to figure out the linear string density pretty easily. So let's quickly, before we go on, let's rewrite this a bit so that the velocity formula is gone. And that's written more clearly in terms of numbers we have. So we know that the velocity of a wave is equal to the square root of the tension divided by the linear string density. And we'll want to use this one because, once again, we effectively have the linear string density and we do have the tension. So we'll be able to sub that in pretty easily. So it becomes 1/2 times the linear string density times the square root of the tension divided by the linear string density times the angular frequency squared times the amplitude squared. Now, although it's minor, there actually is a way that we can simplify this a bit further, because the linear density in the denominator of the square root function will actually cancel out with the linear density on the outside of the radical function. So this ends up becoming written as 1/2 times the square root of the linear string density times the tension in the string, multiplied by the angular frequency times the amplitude squared. So now we have this entire formula written in things that we already have, except for the angular frequency. But that doesn't matter because we're already planning on subbing that in anyway. We're subbing that out so that we have this in terms of the frequency. That is our approach that we're going to use here. And that is equal to the average power. So now let's start algebraically rewriting this formula so that we can solve for the angular frequency. We want to get the angular frequency on its own so that we can then sub in the formula for the regular frequency. So first off, let's bring this half over there. Let's get rid of that half there. Multiply both sides by 2. So that will have 2 times the average power. And then also let's divide by this whole stuff here. Let's divide by both sides by the square root of the linear string density times the tension. And also divide both sides by the square of the amplitude. So let's divide both sides by that. And on this side, those are going to cancel out. We're going to cancel out the square root of the linear density times the tension. And the square of the amplitudes cancel out as well. So then we end up with a formula that is just the angular frequency squared is equal to 2 times the average power divided by the square of the amplitude times the square root of the linear string density times the tension. And let's take the square root of both sides so that we can get rid of that square in the angular frequency there. So now we have a formula that is just equal to the angular frequency is equal to, and I'm actually going to take out the amplitude here because it's already squared. So the square root of that's just going to take it out. So let's write that as 1 over the amplitude times the square root of 2 times the average power divided by the square root of the linear string density times the tension. So now we have the angular frequency on its own. So now let's sub in what we have for the frequency of that. So if we're going to be subbing in the frequency of that, that means that the frequency is going to be equal to the angular frequency, or this whole thing, divided by 2 pi. So in other words, what we're going to want to do now is we're going to divide this entire thing by 2 pi. So because of that, I'm actually, just in the interest of simplification, I'm going to just squeeze the little 2 pi in there with the amplitude. So again, the idea is that we're dividing this whole thing by 2 pi. So this means that the regular frequency will be equal to 1 over 2 pi times the amplitude times 2 times the average power divided by radical tension times the linear string density. So now we have a formula for the frequency in this along the string. So now all that's left to do is to plug in our values. So this is going to be equal to 1 divided by 2 pi times the amplitude. And the amplitude of the string, as it's given to us in the problem, is 7.70 millimeters. But we'll want to write that in meters. So let's write that as 7.70 times 10 to the power of negative 3. So that we have it converted to meters now. And it's multiplied by a radical. So it's going to be 2 times and the average power. And the average power is given to us in the problem as 85.0 watts. So let's write that down. Divided by the radical of the tension of the string times the linear string density. And the linear string density is going to be equal to the mass in the string divided by the length of the string. Because, of course, density is equal to mass divided by volume. So the linear string density is going to be equal to the mass of the string, or 260 kilograms, divided by the length of the string, which is 2.70 meters. And that's the formula for the linear string density. Let's multiply this whole thing by the tension in the string, which is given to us as 36 newtons, or 36.0 newtons. There we go. This whole big thing, let's plug this whole big thing into our calculator, and the answer we get is 197.6 hertz. But let's rewrite this as 3 significant figures so that our answer is consistent, and that answer becomes 198 hertz. And that is the frequency of the string.